All right, hello everybody. We're still doing the review for nonparametric inference. We're doing question 7 now. This is the Kruskal-Wallis test. The H is the test statistic. It ends up being a chi-squared distribution. Remember, we're doing the Kruskal-Wallis because we have 3 populations. The Wilcox only works for 2, so this is analogous to our ANOVA. The following data represent independent random samples. So because they are independent random samples, this is a completely randomized design. It's not blocked in any sort of way. It's coming from these 3 populations. So I have population 1, 2, and 3, and the data is here, right? So the idea is because we have 3 groups, there's really only one type of null and alternative hypothesis for 3 or more groups, and that is there's no difference between the distribution and that there is a difference in at least 2 of the distributions, right? And so now what we're going to do is we're going to specify the rejection region for the test statistic using alpha is equal to 0.25. I think they're using that because the Kruskal-Wallis is always a right-tailed test. So the rejection region is always located in the upper tail of the chi-squared distribution. So I think they're just dividing our typical 5 in half because this is a right-tailed test. So we're gonna come back and do the H, but that's why it's greater than, because it's always in the right-tailed test. We are going to conduct the alpha at 0.25 and get the test statistic, and then we're going to figure out whether we're going to reject or not. So here's what we're going to do. Here is my data, and so I put population 1. I didn't want to make the variables I was worried about that maybe causing an issue with the variable names. So I just did pop 1, pop 2, and pop 3. I put them over here. You can see that, let me do this, that there are 7 values, and 6 values. Because I wanted to do it the way we did it in class with a model version, I actually went ahead and created the sample size for population 1 using the length function. And so you can see it's of length 7. And 2, the sample size for population 2, again, it is 7. And then the sample size for population 3, again, using that length function, and you can see that it is 6 long. And so it is 1 shorter than the other 2 groups, right? Now, the reason I made N1, N2, and N3 is so that I could create a groups variable. And then when I did repeat, I did the repeat function on I, so it would match what we had in the problem. And here I wasn't worried because this isn't an actual variable. This is just text, right? I could just put in NI and it would tell it repeat 7 times, right? And now I'm going to repeat II, its sample size 7 times. And then I could repeat III, its sample size, and that's going to be 6 times. So that just sort of prevented me from having to remember, oh, how long is it? What am I doing there? And so I just have those sample sizes saved, and that made me happy. Creating the scores variable was also super easy. I'm just going to take pop 1, comma, pop 2, comma, pop 3. That's going to put all of these scores in order that I have them in the groups, right? So that makes us happy. So now there are actually 2 ways of doing this, with a model like we did in class and one with a list, which I'll show you next. So with a model like we did in class, we're going to do the Kruskal.test. We're going to do scores tilde groups. Remember the dependent variable, the scores, the ratio interval level data has to go first, and then the categories always has to go second. Now you can see this is a chi-squared test, and our H test statistic is 14,536. There's the 14,536 right there. So we got that. Our degree of freedom is 2, and our p-value is really, really small. Okay. Now we can actually do this with lists. X can be a list. So what I did was I just did list, pop 1, pop 2, pop 3. Okay, with the appropriate commas, and that turned it into a data into the list of prop 1, prop 2, prop 3, and you can see our test statistic is still 1436, degree of freedom 2, and our p-value is exactly the same. So for some of you, like, this is maybe less intense, more straightforward. For some of you, you're used to doing these models, and so, like, this is maybe better for you, okay? But it doesn't really matter because you get the same answer both ways. Now, to actually get the critical value for the rejection region, we're going to use the q chi-squared function. So remember, I'm going to put my alpha in, my degree of freedom in, and because it is greater than, it's a right tail test, we're going to make lower tail false. Now, I actually put alpha divided by 2 here. It's not alpha divided by 2, it's just alpha, okay? So our level of significance that we're testing is the 0.25. So I put the 0.25 in. Our degree of freedom is always second. Our degree of freedom is 2. We had 3 groups. 3 groups minus 1 is 2 groups. So that's right there. And then again, lower tail is false. And when I do that, I get this 7.37. And that 7 makes it an 8. And so if we scroll up, there's our 7.378. And so obviously our test statistic is in our rejection region. And obviously our p-value is much, much smaller than our alpha, and so we would reject the null hypothesis. If this helped you out, give us a like. That makes us happy.